In 11.1, we're looking at reading graphs and linear equations in two variables. Example 1 on page 770 states, refer to the bar graph in figure 1. So here's a picture of the bar graph that's in your books. Which years had sales less than 50,000? So if you look at the bar graph, you first need to note the labels on it. So we have year, which represents my X values, and sales in thousands, which represents my Y values. So the numbers 10, 20, 30, 40, 50 are all by thousands. So which years had sales less than 50,000? So if we look at the 50,000, all the ones that had less were 98, 99, 2000, and 2001. Starting in 2002, it was above 50,000. B says estimate the sales of motor scooters in 1999 and 2001. Okay, so we're going to go look at 1999, and that's going to be about 25,000. And in 2001 was just below 50,000, so maybe about 48,000. Okay, and C says describe the change in sales of motor scooters from 1999 to 2001. So the change is going to be the 48,000 minus the 25,000. So 48,000 minus 25,000 is 23,000. Example 2 says refer to the line graph in figure 2. So again, here's a copy of the line graph that's in your book on page 771. Which year has the greatest amount of Medicare funds? So again, you're going to look at your X and Y axis for the labels. So we have year for my X and funds in billions of dollars for my Y. So which year has the greatest amount of funds? Well, the highest point is in 05. Estimate the projected Medicare funds for 2010. Is there a surplus or a deficit? So we're going to look at 2010. Now notice 0 is not at the corner. Okay, so everything below 0 shows the deficit. It's shaded in pink, and everything shaded in the orange is a surplus. So in 2010, it is just a little bit in the surplus area. And it's maybe about $2 billion. Alright, and see about how projected that funds will decrease from 2006 to 2011. So in 2006, we're at 10 billion. And at 2011, we're right at 0. So if it was 10 billion and then went to 0, that's a decrease of $10 billion. Starting in this chapter, we're going to be looking at linear equations. When we're solving for y or for x, that's part of an ordered pair. So for example 3, we're going to write each solution as an ordered pair. So we find the solution that x is 5 and y is 7. we can write that as 5, 7. That's a point that you would be able to graph. B, if y equals 6 and x equals -1, my ordered pair would be -1, 6. So notice the order. The order is always the x value first and then the y. It's in alphabetical order. Okay, so C, y is 4 and x is -3, so that ordered pair would be written as -3, 4. D, x is 2/3 and y is -12. E, y is 1.5 and x is -2.4, so again we'll put x first, y second, and then F, x is 0 and y is 0. So, and the point 0, 0 represents the origin. Example 4, decide whether each ordered pair is a solution of the equation 5x plus 2y equals 20. So for my ordered pair, remember x is first and then y. So we're going to rewrite the equation with x being 0 and y being 10 to see if it's still true. So I'll rewrite this as 5 times 0 instead of 5 times x plus 2 times 10 equals 20. So 5 times 0 is 0, 2 times 10 is 20, 0 plus 20 is 20. So yes, 0, 10 is a solution of this equation. For it to be a solution, what that means is if I were to graph the line 5x plus 2y equals 20, 0, 10 would be a point on that line. Alright, so I'm using the same equation, 5x plus 2y equals 20, and we're trying to see if the point 2, -5 is a solution. So we'll rewrite my equation. Instead of 5x, that's going to be 5 times 2 plus 2y, 2 times -5 equals 20. So 5 times 2 is 10. 2 times -5 is -10. 10 minus 10 is 0. 0 is not equal to 20. So in this case, no, 2, -5 does not lie on the line 5x plus 2y equals 20. C, 5 times 3 plus 2 times 2 equals 20. 5 times 3 is 15. 2 times 2 is 4. 15 plus 4 is 19, which is not equal to 20. So 3, 2 does not lie on the line either. It is not a solution. Okay, and example D. 5x plus 2y equals 20, so 5 times -4 plus 2 times 20 equals 20. 5 times -4 is -20. 2 times 20 is 40. -20 plus 40 is going to be +20. 20 does equal to 20, that's a true statement. So yes, -420 is a solution. In example 5, we will be given one part of the ordered pair and we'll be looking for the other. So in A, we're given the x value is 5 and we're trying to find the y value for the equation y equals 2x minus 9. So we'll plug in the 5 for x. So this would be y equals 2 times 5 minus 9. 2 times 5 is 10. 10 minus 9 is 1. So y equals 1. So that's my y value for my ordered pair. So my ordered pair is 5, 1. B, I'm given the x value 2. So same equation, y equals 2x minus 9. So y equals 2 times 2 minus 9. 2 times 2 is 4. And 4 minus 9, positive 4, negative 9 is going to be negative 5. So the y value is negative 5, and my ordered pair is 2, negative 5. C, I'm given the y value, and I'm looking for x. So y equals 2x minus 9. I'm going to plug in 7 for y. And I need to solve for x. So I can add 9 to both sides. Divide by 2. And x is 8. So my ordered pair is 8, 7. On D, I'm given the y value negative 13. So this would be negative 13 equals 2x minus 9. And I'm looking for x. So we'll add 9 to both sides. Negative 13 plus 9 is negative 4. Divide by 2. So x is negative 2. So my ordered pair is negative 2, negative 13. In example 6, we're given an equation and a table of values, and we need to complete the table of values. So for A, my equation is 2x minus 3y equals 12. We're given the x value 0, and need to find the corresponding y value. So it's going to be 2 times 0 minus 3y equals 12, and we're trying to find y. So that's 0 minus 3y equals 12. Negative 3y equals 12. Divide by negative 3. So y equals negative 4. Now I need to find all of the values, so I'm going to be working this problem out several times until my table is completed. So now my y is 4, so that's going to be 2x minus 3 times, sorry, my y is 0, 3 times 0 equals 12. So 2x minus 0 equals 12 divided by 2. So x is 6. So one point is 0, negative 4. Another point is 6, 0. We'll work this out again with x is 3. So 2 times 3 minus 3y equals 12. 6 minus 3y equals 12. Subtract 6. Negative 3y equals 6. Divide by negative 3. And y is equal to negative 2. And then one more. This time we have y is equal to negative 3, and we're finding x. So 2x minus 3 times negative 3 equals 12. That's going to be 2x plus 9, because negative 3 times negative 3 is positive, equals 12. Subtract 9. It's going to be 3. So divide by 2, and we get x equals 3 halves. Notice that example B and C, the equations only have one variable. B is just x equals negative 1, and C is just y equals 4, whereas example A had an x and a y in the equation. So when you see equations like these where there's just one variable, that means, for example, in B, x is negative 1, that means x is always negative 1 no matter what the y value is. -1, -1, -1. There's no y in there to change the value of x. So for C, y is equal to 4. That means no matter what, y is always going to be equal to 4. It doesn't matter what the x values are. Okay, in example 7, we'll be looking at points and the quadrants that they're in. So before we follow the example, let's look at a blank grid and number the quadrants. So one way to remember how the quadrants are numbered is if you write the letter C, where you start is going to be quadrant 1. And then as you follow along the C, that tells you the order. So we start in 1 and then it goes to 2, 3, and quadrant 4. Anything that falls on this line is not in a quadrant, but in the x-axis. Anything that falls along this line is not in a quadrant, but on the y-axis. Anything in the center at 0, 0, that point is called the origin. Alright, so let's look at example 7 and go through each of the points. So point A would be located in, if I draw my big C, then A is located in quadrant 2. So 1, 2, 3, and 4. So B is located in quadrant 4. C is located in quadrant 1. D is also in 2, just like A. E is on the y-axis. And F is on the x-axis. Alright, in example 8, we'll be looking at the coordinates and plotting points. So when we're reading ordered pairs, remember that we always read x first and then y. So to plot the points, A is 3, 5. So starting at 0, we'll plot along the x-axis. We'll go to the 3. And then on the y value, which is up and down, so from 3 we'll go up to 5. So it's going to be point A. B is -2, 6. So remember, negatives are everything to the left of 0 on the x-axis or below 0 on the y-axis. So since x is first, we'll go over to the left to -2. And then +6 is going to be up 6. So that's point B. C is -4.50, so -4.5, and then up and down 0, so that's going to be on the x-axis. And 4.5 is between the 4 and 5, so that's C. -5, -2. So over to -5 on the x, down to was D. +6, -2, so now I'm going to go to the right to +6 and then still down 2, just like D. So it's going to be E. F is 0, -6, so that means that when you start at the origin, you're going to move 0 left to right, and you're just going to go straight down -6. So F is on the y-axis. G is 0, 0. That's my origin. And H is -3 and then 5/2. So when we see 5/2, we need to divide 5 divided by 2. So 2 goes into 5 2 times with one remainder. So 5/2 is the same thing as 2.5. So -3 and then up 2.5. and that would be point H. Alright, and our last example for this section, given the linear equation y equals 3.074x minus 6029.7, find the y value for x equals 2002. Round to the nearest whole number. Alright, so there's my linear equation, and we're going to plug in 2002 for x. So we have y in a different color so it's clear. Y equals 3.074 times 2002 minus 6029.7. Okay, so 3.074 times 2002 is 6,154.148. And then subtract 6,029.7, and that gives us 124.448. So the directions say round to the nearest whole number. So 124.4 is closest to 124. Then B says find the y value for x equals 2005 and interpret your results. So again, we'll plug in a formula. Y equals 3.074 this time times 2005 minus 6029.7. So 3.074 times 2005 is 6,163.37, and then subtract 6029.7, and that gives us y equals 133.67. So if we are rounding to the nearest whole number, 133.67 is going to be closest to 134. Alright, so if you look at the context of the problem on the page in example 7, on the main part of the page, it says completing ordered pairs to estimate the number of twin births. So the number of twin births in the United States has increased steadily in recent years. The annual number of twin births from 2000 through 2005 can be closely approximated by the linear equation that we've been using, y equals 3.074x minus 6029.7. So that means that x represents the year, which is what we plugged in. We plugged in the years 2002 and 2005. And y represents the number of twin births in thousands. So on B, where it says interpret your results, these results mean that in 2005, there were approximately 134,000 twin births.